Section 2.4, random variables and their distributions. This is a big section. There's a lot of information in this. Hopefully we can get through a lot right now and really get into it when you come to class. So random variables, the definition is sort of weird. It's a rule associated, I don't know why this is a misprint, but it's a rule that assigns a value to each outcome of the sample space. I'm just going to give you an example of this instead of trying to deal with this definition. All right, so get rid of that word. All right, so here's an example. So let's say we have an experiment. We saw this experiment in class last time, I think. Observe the birth of the first 4 children in the same family. Okay, our random variable might be something like B, which would be number of boys in the 4 kids. All right. By the way, we're going to use capital letters for the random variable, like the description of the random variable, like number of boys, and the values of the random variable. Notice the values of this random variable, B, I'm going to use a symbol here. That means element of this set. 0, 1, 2, 3, or 4. Okay, so B can take 4 values. So, by the way, you might see these lowercase are the actual values, and the uppercase is the description of the random variable. So there's a random variable, okay? So, when we did this, we had boy, girl, boy, right? Boy, girl, boy, boy, right? We'd have things like that. That's one of the elements of the sample space, right? And there were lots of there were 16 elements in that sample space. Well, notice in this case, this specific event where it's boy, girl, boy, boy, that would be the number of boys is 3, right? So for that element outcome of the sample space, this would take the value 3. And there's lots of other things we could ask. All right. Another kind of random variable would be like the weight of a junior Doane choir member, because we know, how they always weigh the Doane choir members. Just kidding. So this would be, maybe capital W could be the weight. And the nice thing is, we're mathematicians. We're not people that are experts in weights of choir members. So when you talk about the value of W, we're just going to say it has to be positive, right? They can't be 0. We don't even have to say the units on this, right? We could say let's do the weight in pounds. Still, we're going to say that the weight of a junior choir member has to be bigger than 0 pounds. All right, so you don't have to be an expert about what the values are. We know that there is a minimum and a maximum probably, but we're just going to say it's definitely positive. All right, so these are different kinds of random variables. Clearly, even the way their values are described are much different, and that difference is the difference between discrete random variables and continuous random variables. All right, discrete random variables take a countable number of values. Countable means you can point at the values and you could start counting them. A countable number could be infinite. You could be counting forever, but you should be able to count them. All right? A continuous random variable takes an uncountable number of values. It's just not discrete. That's how we're going to define it. And I know that's like a pretty, nebulous kind of definition, right? If you haven't ever thought about things that are countable. But notice up on the B, number of boys, 1, 2, 3, 4, right? I can count how many values. This one's discrete, right? But weights, even though we talk about weights, we usually round to the nearest pound. I want you to notice that weights don't have to be rounded to the nearest pound. And in reality, they're not rounded to the nearest pound. You might say you weigh, whatever, 160 pounds. You don't. You weigh something different that's close to 160 pounds, probably. That's the whole idea of continuous random variables. We can't, say what the first value is. We can't even say the next value, right? Unless we're talking about rounding, right? Continuous random variables take an uncountable number of values. All right, let's look at some of the other concepts of this. In this example, we're going to look at this example of the number of, sorry, I'm having a hard time scrolling. Observe, we're going to do the same example with the number of boys in the first 4 children in the same family. Last time we figured out that the probability of having 0 boys, which is all girls, was 1/16. And the probability of having 1 boy, probability B equals 1, was 4/16, and so on, right? We figured out these probabilities. We did a problem similar to this. Well, we can put these values into a table called the probability mass function table. And it would look like this. Probability of B. And notice I'm even using a different symbol here. So notice little b, because it's the values, are 0, 1, 2, 3, 4. Little p of D is the probability of getting that value. So it's a little, instead of this capital B with the brackets, right? And there are the associated values. You'll see that these all add up to 1, right? They're all positive values. They're probabilities, right? And these are the only things that can happen, okay? So those are some of the rules of a probability distribution, is like these have to add up to 1, right? They all have to be positive values. What's the probability, let's see, in part A, what's the probability that there are more than 2 boys in a family with 4 kids? We could write that probability, the symbol for that B is more than 2. Well, notice that's the same thing as B equaling 3 or 4. And I think it's pretty intuitive. Like, I think you know that you probably would add these up. So 4/16 plus 1/16 would be 5/16. That's the probability of more than 2 boys in a family of 4 kids. What's the probability that B is between 1 and 3, including 3, not including 1? So that would be just the values 2 and 3, right? And so for that, that would be 10/16. So notice you can find lots of different probabilities that way. All right, let's continue. So you have a table like this in your packet. It's a big table that shows you kind of a lot of different definitions about discrete and random variables and continuous random variables. We're going to talk about the discrete ones right now. All right, so notice our random variable in a discrete case, x takes a countable number, continuous, x takes an uncountable number. But for the probability function, we just talked about the probability mass function for a discrete random variable. The PMF is what we call it. And we just talked about it's this lower case, and that's just the probability that x takes the value x. So we already know that. We're going to do the continuous part next time. So in other words, if we want to find the probability that x equals a specific value, we would just do P of A, probability mass function of A. So you can fill that out in your table. The cumulative distribution function, capital F of x, this function is defined as the probability that x is less than or equal to value little x. So a cumulative distribution function is always a less than or equal to probability. In fact, we can write that's always true no matter what. It's always less than or equal to. So this would be, the way you would get this is you would do a summation of all of the, I'm going to write P of k values, probability values, where k is less than or equal to x. So in other words, you're just going to add up all the values of the probability mass function that are less than or equal to this value x. That'll be actually pretty intuitive for you. We're going to do it in a second. Similarly, if we wanted to find, this is the discrete side, if we wanted to find the probability that x is between a and b, right, we would add up. So this sum symbol just means add up the p of k values for all k's that are between b and a, including b and a, right? And this one, notice this is just a little different, but you're just adding up the p of k values, the probability mass function values, that are between a and b. In other words, all of these are just add up the appropriate values. That's really what we're seeing with all of those, right? In any case, you're just adding up the appropriate values. All right, the other things we're going to do is calculate means and variances, right? The average value, like the average value of, like the average number of boys in a family with 4 kids. The symbol is mu. That's like a lowercase mu. It looks kind of like a U with a tail on the front, or like a scripty M, I guess. The other symbol is E bracket X, expected value of X. The way you're going to get this is by taking X times the probability of X and add them all up. And that's going to be over all values of X. So notice I'm not going to write from X equals something to something like you were used to in calculus or in other math classes where you use the summation symbol. All right, this just means over all values of X. So in other words, I'm going to put brackets around this for now. We don't really need them, but, right, you're going to take each X value multiplied times the probability and then add them up. All right, this is a really a weighted mean, okay, a weighted average. It's weighted by the probabilities. The variance and standard deviation, so you'll see it says that it's the expected value of x squared minus mu squared. And let's do the expected value of x squared. The expected value of x squared is just like the expected value of x, but with an x squared in there instead. So notice that's the big difference. And then you subtract, after you do this summation, you do subtract the mean squared, and the standard deviation sigma. This is lowercase sigma, is just the square root of the variance. So this is the variance. All right, down below we have the pth percentile. We're actually going to skip it for the discrete case, but we will do it in the continuous case. But let's go see if we can just look at a really quick example before we go. So here we have our example, once again, about the probability, or B being the number of boys in a family, right, of 4 children. If I want to find capital F of 3, that's just a less than or equal to probability. It's the probability that B is less than or equal to 3. So less than or equal to 3, those are the values 0, 1, 2, and 3, right? So if I add those up, that will be 15/16. I got that really fast because I know it's everything except this, right? So I just did 1 minus that. All right, so capital F of 3, right, is just the probability. Somehow this disappeared. Oh, whoops, capital F of 3. Capital F of 3 is probability B is less than or equal to 3, 15/16. Calculate the average number of boys in a family of 3 kids. The average would be multiply the B's times the probability of B. So it'd be 0 times 1/16 plus 1 times 4/16. Right, so I'm taking each value of B and multiplying it by its probability. If I do that and do the calculation, you'll get 2.